But first, how do you find them? Right? How do you find eigenvalues and eigenvectors? Hopefully, most of you probably had this in basic linear algebra, so it'll be a refresh. If you didn't have this, go back and study. You might need it. I'm not going to do it justice. I'm going to do it very quickly. If I have a covariance matrix sigma and I want to find the eigenvalues, the eigenvectors and eigenvalues, I start by finding the eigenvalues, and you do that by solving the determinant equation. So I'm going to take my covariance matrix. I'm going to subtract lambda from the diagonal. Right? I'm going to take the determinant of it, and the determinant for a 2 by 2 matrix is basically the sum of the main diagonal, the product of the main diagonal minus the product of the second diagonal. So it's going to be 2 minus lambda times 0.6 minus lambda minus the terms of the diagonal 0.8 times 0.8. So for a 2 by 2 matrix, that's a nice, simple quadratic equation that you can solve pretty easily. And you're going to get two roots for that equation. There are two values of lambda that result in a 0 for that equation. In this particular case, I get 2.36 and 0.23. So these are my two eigenvalues. Now I can use the property of eigenvectors to find them using these eigenvalues. And the property is, if I take the covariance matrix and I multiply it by my unknown eigenvector, I'm just going to get that eigenvector back scaled by the eigenvalue. So it's going to be longer or shorter, but the components are going to be pretty much the same. So there's my covariance matrix. I multiply it by some eigenvector. These are the two numbers that I want to find, the components of my eigenvector. It's the first eigenvector, so I'm looking for E11 and E12. And what I know is that when I multiply that vector by that matrix, I'm going to get that same vector back, just multiplied by the eigenvalue, 2.36. So that turns into a system of two equations, and after some relatively unagonizing pain, you can you can come out with the following, right? You won't actually be able to solve it. Right? It's kind of interesting. What you will get is you will get a relation between the first component of the eigenvector E11 and the second component. So in this case, it's saying that the first component has to be about twice as big as the second component. It doesn't tell me what the values are. Okay, so well, I could sort of arbitrarily decide that okay, my first component is going to be 2.2 and my second component is going to be 1. Right? And that would work. That is an eigenvector. And if I multiply that by the covariance matrix, I'm going to get 2.36 times that vector back. But the annoying thing is any multiple of that vector would work just as well. So 4.4 and 2 would do the same exact thing. So there is infinite number of vectors that satisfy this constraint. So I'm going to pick one of them, and somewhat arbitrarily for now, and in a few slides it'll become obvious why we want it that way, I'm going to make it unit length. Right? Why unit length? Well, because think about it. What I'm doing is I'm creating a new system of dimensions. Right? So I had x, y, and z, and now I'm creating a new system of dimensions, and ideally I would like my coordinate vectors to be unit length, just so that all the math works out nicely. So I'm going to say that I want the length of this eigenvector to be 1, and that means that you just take this vector and divide it by its Euclidean length, and you come out with those two components, 0.91 and 0.41. So the ratio between them is still 2.2, like this says, and their squares add up to 1. So you have a unit length vector, right? So that is going to be my first eigenvector, the one that corresponds to the eigenvalue of 2.36. And I can do the same thing for the second one. Oh, and by the way, if you divide the two, you'll get the slope of 454, which we had on the previous slide. So I can do the same exact thing to find my second eigenvector, so solve the same system of equations, or you could remember a trick that in 2 dimensions, remember, you're looking for a vector that's perpendicular to this one, and in 2 dimensions there's only one vector that's perpendicular to that, or 2 really. So in 2 dimensions, you can always use the trick of taking your 2 components, flipping them around, and then sticking minus sign on one of them. So 41 goes up there with a minus sign, and 91 goes to the bottom. Or you can solve the linear system and get the same answer. Now, so as a result of this, I get 2 eigenvectors. 0.91, 0.41, and minus 0.41, 0.91. And this is going to be my first principal component in PCA. This is going to be my second principal component.